Averages settle. Flip enough coins, roll enough dice, and the running average calms down toward one number, almost as if chance were wearing off. Last video built the vocabulary for that feeling: convergence in probability, in mean square, and in distribution. In this video, the feeling becomes a theorem, the law of large numbers. The empirical average of independent, identically distributed random variables converges in probability to the mean. The proof takes 3 short moves we have already covered, and the Chebyshev inequality completes the proof. Then a die makes it concrete. The relative frequency of a 6 converges to the probability of a 6. And finally, a warning label. One famous heavy-tailed density refuses to settle at all. Here's the setting. Take a sequence of independent, identically distributed random variables, x1, x2, and so on, each with mean e of x and finite variance. Add the first n of them and call the total Sn, the empirical sum. Divide by n and you get the empirical average, Sn over n. This is the quantity every experimenter actually computes. Measure n times, add, divide. Signal averaging, opinion polls, Monte Carlo estimates, they all live here. The law of large numbers asserts that the empirical average converges in probability to the mean. For every positive epsilon, the probability that Sn over n misses e of x by epsilon or more goes to 0 as n grows. Read the statement slowly. The average is still a random variable, but the probability of a noticeable deviation, however tight you set the bar, vanishes as the sample grows. There are many versions of this law. This is the simplest one, and after last video, its proof costs almost nothing. The proof takes 3 moves, and we own every one of them. First, the mean. Expectation is linear, so the expectation of Sn over n is the sum of the individual means divided by n, and that is exactly e of x. The average is unbiased, it points at the right target for every sample size, and independence played no part yet. Second, the spread. The variables are independent, so their variances add. The variance of Sn over n is the sum of the variances divided by n squared, which collapses to v var of x over n. Watch that denominator work. Quadruple the sample and the variance of the average drops to 1/4. More data buys proportionally more certainty. As n grows, the variance vanishes. And since the expected squared deviation of the average from e of x is exactly this variance, vanishing variance already delivers convergence in mean square. Third, the finish. The Chebyshev inequality from the bounds video converts variance into a tail bound. The probability that the average misses the mean by epsilon or more is at most var of x over n epsilon squared. The right side marches to 0, so the trapped left side must follow. That is convergence in probability, and the theorem is proved. Now make the theorem physical. Roll a die over and over and ask how often a 6 shows up as the number of throws becomes very large. Let dn be the number on the nth roll, and let xn be the indicator that dn equals 6. 1 when the roll is a 6, 0 otherwise. Each xn is a Bernoulli random variable with parameter 1/6, independent across rolls and with finite variance, so the theorem applies. Indicators bridge events and averages. The expectation of an indicator is the probability of its event. The empirical average Sn over n is then the number of 6s divided by the number of rolls, the relative frequency of a 6. Watch it run. Early on, the fraction lurches around, but as rolls accumulate, it hugs the level of 1/6, and excursions outside an epsilon band become rare. By the law of large numbers, the relative frequency of a 6 converges in probability to 1/6, the probability of a 6. The long-run frequency reading of probability, the intuition this whole course has leaned on, is now a theorem inside the axioms. One more scene, because the fine print earns its keep. The theorem demanded finite variance, and a famous member of our gallery of densities fails that condition. The heavy-tailed Cauchy. Its density is gamma over pi times gamma squared plus x squared, and those tails decay so slowly that the Cauchy has no mean and no variance. What do Cauchy sums do? The density of a sum of independent continuous random variables is a convolution, and contour integration, 2 simple poles and their residues, evaluates this one in closed form. Here is the headline: the sum of 2 independent Cauchy random variables is Cauchy again, and the parameters simply add. By induction, the empirical sum Sn is Cauchy with parameter n gamma. Now divide by n. The scaling rule for derived densities compresses the picture right back, and Sn over n is Cauchy with parameter gamma. the very same density for every n, so the running average never settles. After a million samples, its distribution is exactly the distribution of one observation. And the trace keeps taking violent excursions. Averaging buys you nothing here. Nothing is broken. With no finite second moment, the hypothesis of the law fails, so the conclusion is not owed. Finite variance was load-bearing all along. The key idea of this video: averages of independent samples converge in probability to the mean because their variance vanishes like 1 over n. Next, the companion masterpiece, the central limit theorem, where the fluctuations around the mean take on a universal shape.